Hey everyone. Today we're going to break down a statistical tool that sounds kind of complicated but is actually super powerful, the confidence interval. This is what lets us go from just making a wild guess to actually drawing some solid conclusions about the world, all from a tiny piece of data. So, how does it all work?
Okay, so imagine this for a second. You want to know the average commute time for everyone in a huge city. Are you seriously going to go and survey millions of people? Of course not. That's impossible. You're going to take a sample, right? Maybe ask a few hundred people? But how can you be sure that the average from your tiny group is even close to the real answer for the entire city? Well, that's the exact problem we're here to solve. So when you calculate the average from your sample, let's say it's 28 minutes, you get what's called a point estimate. It's your single best guess. But let's be real here. It's just a guess. It's a great starting point, but it's fragile. The odds of that number being the exact true average for the whole city are practically zero. And this is where the upgrade comes in. Instead of a single number, which is like trying to hit a tiny bullseye from a mile away, a confidence interval is like casting a big net. It gives us a whole range of plausible values. It's just a much more honest and frankly way more useful way to represent what we know. So what's the official definition? A confidence interval is a range calculated from your sample that you can be pretty sure contains the true value for the entire population. That true value we're hunting for is called the population parameter. The whole point is, we're building a net to catch the real answer.
Now you are going to see this number everywhere, the 95% confidence interval. It's pretty much the industry standard in a ton of fields. But what does it actually mean to be 95% confident? It's a little more subtle than you might think.
Okay, this is the key. Being 95% confident isn't about any one specific interval you calculated. It's all about the method you used. Think of it this way. If you were to repeat your survey 100 times, each time with a new random sample, you'd expect the true average commute time to fall inside your calculated range about 95 of those 100 times. So it's about the reliability of your process. So how do we actually build one of these things? It might look like some complex math is coming, but really it's just a simple recipe with a couple of key ingredients. Let's break it down. It's a super simple three-step process. First, you start with your single best guess. That's your point estimate. Then you calculate something called the margin of error. This is the secret sauce. Finally, you just add and subtract that margin of error from your guess, and boom, you have your upper and lower limits. That's your interval. So, what goes into that margin of error? Really, just two things. First is a critical value, which is a number that's tied to how confident we want to be, like that 95%. Second is the standard error. You can think of this as a measure of how much your sample average would bounce around if you took a bunch of different samples. It's all about how variable your data is and how big your sample is. And here's what that recipe looks like as a formula. You see our point estimate and then the plus or minus sign. And right after that is our margin of error, the critical value multiplied by the standard error. This little engine is what builds the whole thing. All right, enough theory. The absolute best way to understand this is to actually see it work. So let's jump into a real example and build one of these from the ground up. Okay, here's our setup. Let's say we know the population standard deviation is 40. We've got a solid sample size of 400, and we're aiming for that classic 95% confidence level. Time to calculate that margin of error. First up, we need our critical value. And here's a little pro tip. For a 95% confidence interval with a large sample, this value is always the same, 1.96. This number comes from something called the z-distribution, and honestly, it's a great number to just lock away in your memory. Now we just plug in the numbers. We take our critical value, 1.96, and multiply it by the standard error. Remember, the standard error is just the population standard deviation, that's 40, divided by the square root of our sample size, which is 400. And when you run that math, you get 3.92. That's it. That's our margin of error. So whatever our sample average was, we would just add and subtract 3.92 to create our 95% confidence interval. Pretty straightforward, right? So this leads to a really good question. If we can be 95% confident, why don't we just crank it up to 99% or even 99.9% all the time? I mean, it seems like being more confident is always better, but there's a hidden trade-off. The level you choose really depends on the consequences of being wrong. If you're doing medical research where a patient's life might be on the line, you just can't afford to be wrong. You're going to demand 99% confidence. But for a simple market survey about, say, a new soda flavor, the stakes are way lower. 95% confidence is probably more than enough.
Okay, before we wrap this up, I've got one last crucial pro tip for you. It's a simple rule of thumb that tells you which statistical tool you need to grab to find your critical value.
It all comes down to your sample size. The magic number is 30. If your sample size, or n, is bigger than 30, you use the z-distribution, just like we did in our example. But if your sample is small, less than 30, the math changes a bit and you have to use a different tool called the t-distribution. It's a really simple but critical distinction.
So let's end on this final thought. To be more confident, to cast a wider net, we have to make our interval bigger. For our commute time example, a 95% interval might be between 25 and 30 minutes, but a 99% interval might be between 23 and 32 minutes. We're more sure the true answer is in there, but our estimate has become a lot less precise. And that's the constant trade-off in statistics. You're always trying to find that perfect balance between confidence and precision.